Good morning, boys and girls, and welcome back to our last lesson on polar area. Let's first go back and let's review how to find the area of a circle and the area of a sector. To find the area of a full circle, we all know that you would do area as pi r squared. But if we just wanted a piece of that circle, a piece of our pizza, pizza pie, if we just wanted a piece of that circle, then we call that a sector. And to find the area of a sector, our formula looks a little something like theta over 2 pi times pi r squared. Again, where this is coming from is I'm trying to find the percentage of the circle and then multiplying by the area of the whole circle. I know that to get all the way around the circle, all the way around is 2 pi. So if I just take that theta of that angle of my circle and divide it by 2 pi, that would give me the part of the circle that I'm looking for, and then I multiply that by the area of the full circle. Or if I simplify this, I get 1/2 theta r squared. All right. Now we're going to play with this a little more in 1 second here. But now let's look at like a polar graph maybe that I'm going to have to find the area of. Okay, so we have some curvy polar graph like the one kind of drawn here, and I wanted to find the area inside that polar graph. The way we're going to kind of approach it is we're basically going to find the area of a bunch of sectors. Here I have just one of those sectors drawn now. One, theta r, with a radius of r sub 1, and another different theta with radius r sub 2. But this would just be one of those, one of those sectors. And what we want to do to get our area the best, again, is we're going to shrink, the theta between these. I'm going to try to shrink that to 0. Okay? So coming back to our formula here, if I shrink that to 0, this more or less becomes 1/2 r squared d theta, again, because I'm shrinking that, that distance to 0. This theta here to 0. All right, so we're going to try to find the area of a polar region between two radial lines. Theta equals alpha and theta equals beta. So up here, like in the green, alpha to beta. Basically, we're going to find a bunch of little sectors, an infinite number of sectors with the theta goes to 0. And so we would use this formula we've kind of modified. So area is 1/2 the integral alpha to beta of r squared d theta. I pulled that 1/2 out in front. And so, I don't know, my weak attempt of the proof or justification of our formula for the area of a polar region is right there. So hopefully kind of get some idea of where this formula is coming from. But we are just now going to have to use this formula to find the area of a polar curve. All right, so here we go. We want to find the area of the cardioid r equals 1 minus cosine theta. Okay? So again, if I'm going to have to do this problem, I think to graph it would help if I don't have a graph. And so here's a quick review / easy way to graph your polar functions. When you do this, you want to know a couple things. You want to know when the r is equal to 0, and you're going to find your r at the other main points like 0 and pi over 2, 3 pi over 2, 2 pi, so on. Right? And what I tend to do is just try to make a little table that I'm going to graph from. Like this. And even though we write this like r and theta, again, I tend to plug in for the thetas to try to find my r. Again, but I always start first with this r equals 0. I'm going to find out those thetas so I know to include those as well as my other ones on my table. So in this case, 1 minus cosine theta, my r, is going to equal 0 when cosine theta equals 1. And in this case, that's at 0 and 2 pi. So those are already ones that I'm considering up here. So I didn't really, I guess, have to do that in this step. But it's a good place to start when it's not that case. All right. So the thetas I want to evaluate for are going to be 0 and pi over 2, pi, 3 pi over 2, and 2 pi. And again, generally, just if you go one revolution of your circle, 0 to 2 pi, that should get all the ones you need. If you need more, I could always go and add more and pick up, 5 pi over 2 and 3 pi and so on. All right, but now I want to find these r values that correspond with these thetas. So I'm going to plug these thetas into our equation for r. R equals 1 minus cosine 0. Cosine of 0 is 1, so 1 minus 1 is 0, and we kind of do that from our solving over here. R equals 1 minus cosine pi over 2. Cosine of pi over 2 is 0, so 1 minus 0 is 1, and so on. I'm going to go and find all my r values that correspond with those thetas. And then once I have those, I can go ahead and I can sketch these points. So again, to sketch the points on a polar axis, a little bit weird kind of review again here is, I always, again, start with a theta. I start with my angle that I need to go to. Okay, in this case, the angle is 0. So 0 is right here along this axis right there, right? And I'm going to do a radius of 0. So a radius of 0 would mean I am at the pole, at the origin, at the pole it's called. So I'm going to start right there. That is my first point. Okay. Now I'm going to go to the point 1 comma pi over 2. So 1 pi over 2 is up the y-axis, the old y-axis, but now it's up here, right? And I'm going to do a radius of 1. Okay? So I'm going from 0, 0 from the pole to 1 over pi over 2, and again, so that just kind of becomes a little, I kind of just jump, loopy it, okay, just to give me a rough idea what it's going to look like. Now I need to go in the direction of pi. Pi is along the, again, what we'd call the negative x-axis. Pi is over here. And I need to go out 2 in that direction. So I'm going to go out 2 in that positive direction. And so now, again, I'm going to loopy it kind of like that. And then now 3 pi over 2 is down the negative, again, what we call the negative y-axis. And if I go a radius of 1, it'd be down to there. And again, I just kind of loopy it. And then now, again, I'm going to go back in the direction of 2 pi. 2 pi is the same as 0. But, again, my radius is 0, so I'm back to the pole. And there's a quick sketch of a cardioid, okay? That's what this graph would look like. And I'm going to try to find the area inside of this cardioid. Okay, so to find the area inside this cardioid, what we're going to do is we're going to use, again, that formula. Area is 1/2 alpha to beta of r squared d theta. And now what we're going to do is, again, alpha is where I start and beta is where I stop. So in this case, to graph it, we started at 0 and we ended at 2 pi. It took me from 0 to 2 pi to get all the way around and make my shape. And careful, don't forget your 1/2. I almost forgot my 1/2 and I just squeezed it in there. Hopefully you saw it pop up. And then now I just need to do my radius squared. In this case, our radius is r minus cosine theta squared d theta. So that is going to be the setup to find the area inside of here. Area is 1/2 integral 0 to 2 pi 1 minus cosine theta squared, that quantity d theta. And to evaluate this, again, a lot of times it's just calculator, so I would plug this into my calculator, and you should get something like, the area is 4.712, or approximately 3 pi over 2. Okay? Which, this kind of just reminded me, I probably should show you how to graph some of this stuff on our calculator as well here. Just like we talked previously, your calculator, we talked about the sequence mode. Your calculator also has a polar and parametric mode. I don't really use the parametric mode very much, but I do use the polar mode a little bit. If we hit the mode button, if we go down here, you can see there is a function mode, parametric mode, and a polar mode, and then a sequence mode, right? We talked about already. But I'm going to go to polar. And if I go to polar, now I want to hit y equals. Notice all of your things are like r equals, r equals, r equals. And if I hit the x button, it actually gives me a theta now instead of x. We are now in polar mode. So if I wanted to graph what we just looked at, I would do 1 minus cosine theta. Again, do make sure that you are in radian mode when you do this as well. And graph. That's kind of hard to see, so sometimes I do like to zoom trig, zoom number 7. But you can see there's that, you know, maybe not as good as our drawing, but there's a graph of that cardioid that we just had, all right? And just like in the other part, I can do, you know, I can plug stuff in 1/2. Make sure you plug that in first, that coefficient, and then your, you know, math 9 to get the integral from 0 to 2 pi. And then I just got to plug in my r, 1 minus cosine theta, again in parentheses squared, then my d theta, and see, we get our 4.7123, 4.712, right? And again, if you would, you could work this out by hand, I think, if using use that, maybe not, maybe we can't integrate this one by hand, but if you did, it would equal 3 pi over 2. That's 4.71238898. All right, so there's our first example. Again, how you can kind of graph a polar function and then find the area both via calculator And again, if you have to graph these on your calculator to get an idea, that's good. But you kind of need to be able to do it by hand so that again, this is where we're going to get our limits from, and that's where it's kind of important. Okay, next and last one. We want to write an integral for the shaded region in the graph below given by r equals cosine 2 theta. So again, r equals cosine 2 theta is a rose, is a flower, right? And we want to find the area of just one of these petals. Now, if I just wanted the area of the petal, all the petals are going to be congruent, right? Again, my sketch might not look that way, but all the petals would be the same size. But since they're asking for a specific petal, I kind of got to think about going back and regraphing this so that I get my limits correct on this thing. So again, to graph this, if we're going to think about graphing it, I'd want to find out where all my r's are 0. Okay, so I said r equals cosine 2 theta equal to 0. And then I'm going to use to find the important thetas. And then I'm also going to use all the thetas like 0, pi over 2, pi, 3 pi over 2, 2 pi, etc. So cosine 2 theta is going to equal 0 when that angle is pi over 2, or 3 pi over 2, 5 pi over 2, 7 pi over 2. And I got to carry that out a little bit because when I go and divide by 2, I'm going to get theta has to be pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And again, I want all the angles that are between 0 and 2 pi. So those are all the ones that would be between 0 and 2 pi. All right. So now I'm going to set up my table. And again, I would use the thetas for 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, so on, right? But you'll see, I think these are all the ones we're going to need for this picture right here. So if I start plugging all these thetas into r equals cosine 2 times 0, r equals cosine of 0, I get 1. R equals cosine 2 times pi over 4 is pi over 2, cosine of pi over 2 is 0. Or I guess all the ones we already found, we know these are going to be 0 at all the pi over 4s, since that's what we solved for. So we're going to have to evaluate just these other ones. If I plug in pi over 2, 2 times pi over 2 is pi, so cosine of pi is negative 1. And cosine of 2 pi, if I plug in pi, is 1. So again, this table here, we get these values here. And so now if I were to kind of sketch these points, we would start with a theta of 0, so in this direction here, and a radius of 1. So we're starting right there on our petal. And then I'm going to go to pi over 4 and a radius of 0. We're back to the pole. Then pi over 2 and a radius of negative 1. So this one went from here to here. And then pi over 2 is the positive y-axis, but I'm doing a radius of negative 1. So that would bring me down here. All right. Then I'm going to go to 3 pi over 4, radius of 0. 3 pi over 4 here, but a radius is in this direction here, right? But again, radius of 0 brings me back to the pole. And then I'm going to go to pi, positive 1. So pi again is over here, radius of positive 1 would be that right there. So right here we are starting our petal, right? And then 5 pi over 4. Sorry about that, boys and girls. I wasn't watching. Hopefully that wasn't too loud in your ears. But now 5 pi over 4 back to 0. That is that second part right there. So my petal, this petal that we're talking about, is really from there to there. And you can kind of see the way we're kind of graphing this there. If you graph this on your calculator, it's going to go in that same order. If I graph r equals cosine 2 theta, I think I've adjusted my window here, but it's going to follow that same path we did because it's doing the same thing we did. It's plugging in all these critical values. So that's kind of neat. And again, so that's what we need to do to find our one petal, the one we're talking about. Now that we have that, we're ready to find our area. Area is 1/2 integral. We started at 3 pi over 4, and we're going to 5 pi over 4 of our radius, cosine 2 theta, squared d theta. All right? And in this case, we just had to write the integral, so we are done. But the hard part again was finding that, that region right there. All right, boys and girls, that is the basics of finding the area of a polar region. And if you got questions, hit me up. Otherwise, see you later and have a great day.